Hi everyone. In the next couple of videos, we're going to look at Chapter 14. Chapter 14 is very similar to Chapter 13. The first part, we're going to look at sampling distributions, and the second part at confidence intervals. The difference is this time we're going to be looking at means or averages instead of proportions. So I want to start with just reminding you all about the notation for a population mean and standard deviation versus a sample mean and standard deviation. When we're talking about the population mean, we use mu and the standard deviation is sigma. So we use Greek letters when talking about the population. When we're talking about the sample mean, sample, not simple, when we talk about the sample mean is x bar, and the standard deviation is s. Sometimes there's a little x, sub x after this, like in your calculator, but if you see an s, that's a sample standard deviation. So we're going to start by looking at the sampling distribution of sample means, with the idea that every time we take a sample and we calculate the mean of that sample, we're going to get a different mean than another sample where we calculate the mean. Right? Every sample is going to give us a different mean, a slightly different mean. And that means that these sample means are a random variable and therefore have a sampling distribution. We want to look at that sampling distribution and see how it compares to the population so we can look at the pattern and therefore use that pattern with confidence intervals when we only have one sample to work with. So the pattern for our sample means is called the essential limit theorem. And I have an applet that I made a video with that I think it explains best what you see without showing you just a whole bunch of data. So I have the video here. I can't actually play it within these slides in this way. I don't really know why, but it's not quite working. So I'm just going to go and do just a quick rundown of what this applet does, but please also watch the video that I have of this. So this is what the applet looks like. The top graph gives the population distribution. So you can see here that the population distribution is normal with a mean of 16 and a standard deviation of 5. I want to look at what happens when we look at a sampling distribution of means when the sample size is 25, and also for the mean when the sample size is 5. So what this applet's going to do is it's going to animate the process of taking a sample of 25, calculating the mean, and then plotting that mean. So it's taking a random sample of 25 data points from the population, calculating the mean, and then plotting that mean. And that's doing the same thing for size 5. Notice that these two samples gave us different sample means. That's perfectly okay. It doesn't mean that there's anything wrong, and it has nothing to do with their sample size. This is just natural sampling variability. If we do this again, it's taking a random sample of 25. It's going to calculate the mean of these 25 data points and plot that mean value. And then it does the same thing for the 5. And notice that already you can see that the smaller sample size has more variation between the sample means. So I'm going to kind of jump ahead because you can watch this video later on. But if I do lots and lots of samples, so I'm going to do 10,000 samples for each of these, you can see that both of these distributions are fairly normal. They're unimodal and symmetric. And the mean of the distributions is the same as the population mean. So if you look over, I can't write on this page, but if you look over to the left, the mean for the samples of size 25 is 15.99, and the mean for the samples of size 5 is 16. And remember that the mean for the population was 16. The difference between all of these is that the population is the most spread out, has the most or the highest standard deviation. And then the samples with the largest sample size has the least amount of deviation from that mean value in the middle. So the larger the sample size, the less variation from the mean. But the mean of these sampling distributions gave us the population mean. There's also a pattern with the standard deviation, just like there was with proportions. So there's an extra little piece when we talk about sample means. If you'll notice, I keep bringing up the population distribution, which we didn't talk about with proportions. But we are talking about it with means because the sample size is going to be dependent on the distribution of the population. When the population is normal like this, it really doesn't matter what size sample you work with. But if I were to change this to be a skewed population, then I can tell you right now that a sample size of 5 is not big enough. The pattern's not going to work out. So I'm going to turn that off. And we're just going to look at samples of size 25. So notice that with this skewed distribution, the mean is 8.08. I'm going to skip the whole animation and just create 10,000 samples. And you can see that even though the population distribution is skewed, the sampling distribution is unimodal and symmetric. And still, the mean of the sampling distribution is the same as, or very close to, the population mean. So let's go back to the slides. What this is saying is that the mean of the sampling distribution, so the mean of all the means is the population mean. I know that's kind of crazy. And the standard deviation of all of the sample means is the standard deviation of the population mean divided by the square root of n. And you can actually see that in the video with this applet. The other thing that we learned is that when the population distribution is normal, then the sampling distribution for X bar is also normal for any size sample. But when the population distribution is not normal, we need a sampling distribution that's large enough. Now the applet didn't let me do anything that is actually considered large enough by our textbook, which is greater than or equal to 30. For these sampling distributions of means, the same conditions, the same 3 conditions in the beginning, these are the same as those for the proportions. So we need to have a random sample. We also need to have the 10% condition, which says that the sample size is not more than 10% of the population size. And we need these 2 conditions to hold so that we can safely assume that the individuals within our sample are independent. The one different assumption and condition with proportions, we had that success-failure condition where the number of successes and number of failures had to be greater than or equal to 10. But when we're talking about means, that's different. We're talking about means, we're saying that the sample size has to be big enough. So we go back to that idea that if the population distribution is normal, then the sample size can be anything really. But if the population distribution is skewed, then we need a sample size that's 30 or bigger. The biggest thing is normally you don't know what the population distribution looks like. So if you don't know what it looks like, you have to assume that you need a sample size that's 30 or bigger. So let's look at a couple of examples. So it says recent data from the U.S. Census indicates that the mean age of college students is 25 years with a standard deviation of 9.5 years. A simple random sample of 125 students is drawn. We're going to check the assumptions and conditions. We have a random sample. It says so in the problem. And 15, that's not 15, that's 125 is my sample size. So this should say 125. 125 is still definitely less than 10% of all college students. And I just probably wrote over it, yeah. So since these two conditions hold, then we can safely assume that the individuals within our sample are independent. The big one is the last one, to make sure the sample size is big enough, and the sample size of 125 is way more than 30, so it's big enough regardless of what the population distribution looks like. So we now want to describe the sampling distribution for X bar. Since all of these conditions and assumptions hold, we know that the sampling distribution is normal, and that the mean of the sampling distribution, so we're looking for the mean and the standard deviation of the sampling distribution. The mean of the sampling distribution is the same as the population mean, and they told us that was 25. The standard deviation of the sampling distribution is the standard deviation of the population divided by the square root of the sample size. So in this case, it's 9.5 divided by the square root of 125. The most common mistake that I see with these problems is that people don't adjust the standard deviation. They just use 9.5. But that's from the population, not the sampling distribution. And when we do that calculation, we get 0.85, which means that we have a normal model with a mean of 25 and a standard deviation of 0.85. Notice how different the standard deviation of the sampling distribution is compared to the population distribution. Right? The standard deviation of the population is going to be large, 9.5, that's big. But the standard deviation of our sampling distribution is less than 1, 0.85. So we're going to use this to answer very similar questions to what you saw in Chapter 13, and then again also what you saw way back in Chapter 5. The first questions are asking for the probability. And regardless of if we're talking about a population or a sampling distribution of proportions or a sampling distribution of means, if it's a normal distribution and it asks what is the probability, then we are using the normal CDF command. This is asking for the probability that the sample mean age of students is less than 22. So if we take a sample of 125 students, what is the probability that we will get a mean that is less than 22 years of age? So we're going to go from negative infinity as our lower bound to 22 as the upper bound, and then use the mean and standard deviation that we found for the sampling distribution. I picked this problem because I really want you to see what happens in your calculator. So if you're watching this video, please put this in your calculator quickly, because I want you to see that what it's going to give you is 2.08 with a bunch of other numbers, and then if you look at the very end of those numbers, you'll see an E -4. We're finding a probability here, and you know that probabilities are between 0 and 1. So the answer is not 2.08. We can't have a probability greater than 1. What's happening is that this probability is so small that your calculator is writing it in scientific notation. And this e to the -4 means 10 to the -4 power. With scientific notation, it means that we back up the decimal point 4 spots, which means we're going to have 3 zeros in front of this 2. So this number is actually 1, 2, 3, and there's the 4th spot that we moved, 0.8. So it's a very small probability, but don't round this to 0. A probability of 0 means there's absolutely no chance that this could happen, but that's not what's happening here. There is a chance, it's just really small. The next question is similar. It's asking for a probability again, so we're going to use normal CDF. And this time it's asking that it's greater than 27. So now our lower bound is 27 and our upper bound is positive infinity. But we're using the same mean and standard deviation that we found for the sampling distribution. When you put this in your calculator, you're going to get 0.0093. Again, another pretty small probability. The next two questions are inverse norm questions. And I know that because it's asking me about a percent, and I'm trying to be careful because I know that this is confusing when you talk about proportions. But when it's talking about a percentile or it's talking about an upper area under the curve, like the top 10% or the lower 5%, then we're looking at an inverse norm command. Percentiles are automatically left areas, so whether or not you have the new calculator or the older calculator, you're going to use 0.3 here. You don't have to adjust anything if you have the older calculator. And then still use the mean and the standard deviation from the sampling distribution. If you have the newest calculator, make sure you choose left as the area, since this is a left area. And we will get 24.55. This is not a percent. This is a sample mean. This is an X bar. This is saying that getting a sample mean of 24.55 when the sample size is 125, that there's a 30% chance of seeing that sample mean or something smaller. The next problem asks for the cutoff for the top 10% of sample means. And this is where, because this is a right area, if you have an older calculator, you have to adjust the area that you're entering. So if you have the newest calculator, you can keep it as 10%. Just be sure to switch the area to right. If you have the older calculator, you want to make sure that you adjust this to be a left area. So we subtract it from 1 and write this as 0.9. Either way, you're going to get an answer of 26.1. And again, this is a sample mean. When you're looking at these problems and you're looking at your answers that you're getting with the inverse norm commands, see if the answer that you're getting is lining up with what the question is asking. We know the 50th percentile is going to be 25, right? Because 25 is right in the middle. So if they're asking for the sample mean for the 30th percentile, you know it's going to be smaller than 25. And if they're asking for the sample mean that's for the top 10% of samples, you know it's going to be bigger than 25. So I have one more example here that I want to go through. And I'm going through this example because it's similar to one that you have in your written homework that a lot of people get wrong. So now I'm hoping that a lot more people get it right. So this problem is all about the conditions that need to exist in order to apply the central limit theorem. So it says home prices have jumped considerably during the pandemic, increasing by almost 10% in the last year. In Maryland, the distribution of home prices is skewed right with a mean of $346,000 and a standard deviation of $52,750. Explain why we cannot determine the probability that a randomly selected home in Maryland costs more than $360,000. So with this problem, with this first part, we're talking about a single home. The probability that a single home costs more than this amount. But if we're just talking about a single home, then we are talking about the population distribution. And we're told that the population distribution is skewed right. If it's skewed right, then we can't apply the normal model to that distribution. And if we can't do that, then we can't find the probability. So we would say that since, I don't know, did I write these in? Oh, I did. So I have that the population distribution is skewed, so we can't be modeled with a normal model, and therefore we cannot determine the probability of observing any one data value. For the next part, it says, can we estimate the probability that a randomly selected sample of 10 homes in Maryland will have a mean cost more than $360,000? So now we've shifted from talking about an individual home to talking about a sample of homes, which means we want to know, is the sampling distribution normal if our sample size is 10, right? A sample size of 10. Well, since the population distribution is skewed, I need a sample size that's bigger than 30. So a sample size of 10 is too small, and we would say, no, the sample size is too small since the population distribution is skewed. If the population distribution was normal, the sample size can be anything. The last part says, can we estimate the probability that a randomly selected sample of 50 homes in Maryland will have a mean cost more than $360,000? So now we do have a sample that's larger than 30, and therefore it is possible for us to calculate the probability because the sampling distribution will be normal. So we'll say, yes, the sample size is large enough to use the normal model to approximate the sampling distribution for X. And then it says, so if so, what is the probability? So I'm actually going to show you kind of a shorthand way to do this. We know that we're working with the normal model. We know with the normal model, if I'm finding the probability, we're going to do normal CDF. We're looking for a cost of $360,000 or more. So the lower bound is $360,000. Don't put the comma in there. The upper bound is infinity, and since this value, this 360, is so big, make sure you use a lot of 9s here. Like 3 or 4 is not going to cut it. You have to make sure it really knows its way up to infinity. The mean of the sampling distribution is the mean of the population. So the mean here is the same as what's given above. But the standard deviation is not the same as the standard deviation of the population. The standard deviation is the standard deviation of the population divided by the square root of n. So divided by the square root of the sample size, 125. You can actually put this into the normal CDF command. You can put this little formula in, and it will calculate it for you without having to do the extra calculation. And when you do this, you get, where'd it go? Oh, 0.03. Okay, the next video will be on confidence intervals.